Now that we have successfully completed an example or two about performing significance tests for population proportions when it's a one-sided test, let's look at two-sided tests. So the result of a significance test is basically a decision either to reject or fail to reject your null hypothesis. When we reject the null, or h sub 0, we're sometimes left wondering what the actual proportion p might be. Now, a confidence interval might shed some light for us on this issue. So a 95% confidence interval gives an approximate range of p sub zeros that would not be rejected by a two-sided test at the alpha is 0.05 significance level. Now, a 90% confidence interval gives an approximate range of p's that would not be rejected by a one-sided test at the 0.05 level. Now, the link here isn't perfect because the standard error used for the confidence interval is based on the sample proportion p hat, while the denominator of our test statistic, z, is based on our claim proportion from the null hypothesis. So we're going to do an example here, and we're going to go through both the significance test and the confidence interval and see how they compare. When the accounting firm AJL and Associates audits a company's financial records for fraud, they often use a test based on Benford's law. Benford's law states that the distribution of first digits in many real-life sources of data is not uniform. In fact, when there is no fraud, about 30.1% of the numbers in financial records begin with the digit 1. However, if the proportion of first digits that are 1 is significantly different from 0.301 in a random sample, the Associates does a much more thorough investigation of the company. Suppose that a random sample of 300 expenses from a company's financial records results in only 68 expenses that begin with the digit 1. Should they do a more thorough investigation of this company? Alright, so important information in this problem. 30.1% was important. Sample of 300. 68 would be our x in this case. And it says if it's significantly different. So not more, not less, just different. So that's going to help us write our alternative hypothesis. So let's go ahead and start. First step is state. In phantoms, we need to say what our parameter is, and then also what our hypotheses are. They didn't give us an alpha, a significance level, so we're going to assume to use 0.05. We want to test the following hypotheses at the alpha equals 0.05 significance level. Our null, this is a proportion problem, so we use p. They're claiming that the proportion is 0.301. And we want to test to see if it's different than that. So not equal to. So either more than or less than, so we simply write not equal to. Where p is the true proportion of expenses that begin with the digit 1. Okay, so we've taken care of the first two in phantom state. We have our hypotheses and our parameter, also including our significance level. In our plan, we have to say the type of test that we're doing. So we're going to perform a one sample z-test for p as long as our conditions are met. If our conditions are met, we'll perform a one sample z-test for p. Go ahead and go through and check off all of your conditions for this. I'm going to pause this and write them out so I have enough time in the video. You go ahead and try to do it first before you see how it's all worked out. We have a random sample of expenses. Both our n times our claim and n times 1 minus our claim is greater than or equal to 10, so we can assume it's normal. And we check the 10% condition for independent, which means we'll be allowed to calculate our standard deviation here in a moment. So next comes the do. where we do the math. All right. We need to specify our p-hat in this case. They didn't give it to us explicitly. So we have to calculate. 68 is our x. 300 is our n. 68 out of 300. Let's round to 3 decimal places here. 227. So our test statistic z, you take your p-hat, 0.227, and that's the only time it's used in this whole formula. Everything else that we use comes from the claim. So 0.301, and then the standard deviation is also found by using 0.301 all over 300, not 600. Okay. Now, I'm going to go ahead and just put this information in my calculator. So, I'm going to go to tests. Remember how we did this? So I go to stat, I go to tests. We're picking option number 5. That's why the name is so important. So one sample proportion z-test. Our claim here was 0.301. Oops, 301. X was 68. Sample size was 300. And this is a two-sample, or two-sided. So we do the not equal to. Calculate. My z here is negative 2.8. Let's see. Yeah, negative 2.806. And then my p-value, according to my calculator, is 0.005. Now, I want to show you how you would have done this if you forget to do this in your calculator, the quick p-value. What you would have had to have done is you would have to go into second vars, normal CDF, and then since we don't know like lower upper, since it's a negative test statistic, it's going to be like a left-tailed to the left. So we're going to have some small value for my lower, negative 2.806 for my upper. And that gives me, if you can see, 0.0025, but the calculator said the p-value is 0.005. That's because this is a two-tailed. So that p-value is both of those tails together, so you just have to double that, and that's where they get 0.05. Alright? So when it's two-tailed, if you're doing it by hand, you got to double it, otherwise just use what your calculator tells you. So this is a very small p-value compared to our alpha. So let's go ahead and come to our conclusion. Since our p-value is smaller than our significance level, we're going to reject our null. So there is convincing evidence that the proportion of expenses that have a first digit of 1 is not 0.301. So therefore, the AJL and Associates should do a more thorough investigation of this company. So there's our conclusion. Remember, we state all three things. Compare your p-value to your alpha. Say what you're doing with the null. Come to a conclusion. Either there is evidence or there's not enough evidence in support of your alternative hypothesis. Always including the context as well. Now, we're rejecting it. So we're saying it's different than 0.301. But what might it be? What might the true proportion be for this company, right? In the sample, we saw that it was 0.227, which is clearly different. But how different is it? So this is where a confidence interval comes in. So we're going to construct a confidence interval. So taking it back to what we learned in Chapter 8. So we're going to take the exact same information now and do a confidence interval. So let's go ahead and go through that. Full 4-step process. What do we want to do? Because it was a 0.05 significance level, we're going to use a 95% confidence level. 95%. So remember, when we're doing significance testing, we use the acronym PHANTOMS. When we're doing a confidence interval, we use the acronym PANIC. First P stands for your parameter right here. A is assessing your conditions, and then the n is naming the interval, and that all happens in the plan step. So we'll use a one sample z interval now, not a z-test, because we're doing confidence interval, for p. So let's check our conditions. Random, yep, we did that from the last one, so I'm kind of breezing by this. Normal, we do need to check, and the difference between checking your condition in your significance test versus in your confidence interval. Confidence interval, you're using your p-hat, right? So I got to check n times p-hat. So 300 times 68 over 300, which is 68. And then n times 1 minus p-hat, and that gives you 232, which is also greater than or equal to 10. So that condition is met. Independent is the exact same as the last one, checking that 10% condition, okay? If we were doing this from scratch, we would want to write this all out, but because we just did it on the previous example, I'm not going to write it all out again. So, the do, we need to use our formula. So, remembering from way back when, we start with our statistic, times it by our critical value, or add or subtract my critical value, I should say, times my standard error, using again that p-hat value, so 0.227. The critical value for a 95% confidence interval is 1.96, if you remember that. It's also on that table. All of this is using 0.227. Notice how we're not using 0.301 anywhere in this problem. So that's one of the differences. So your interval is 0.180 to 0.274 when you do those calculations. Okay? So let's come to a conclusion here. We are 95% confident that the interval from 0.18 to 0.274 captures the true proportion of expenses at this company that begin with the digit 1. Now remember back to our significance test. They were claiming that it was 0.301. 301 is not in this interval. Okay? That's why we rejected the null. It wasn't a plausible value. So it made me think, it's probably not right. So that's why we rejected our claim. It's not in the interval. So we can use confidence intervals to come to the same conclusion we did using significance testing, but only if it's a two-sided test. So only when your null or your alternative hypothesis is a not equal to. If it's just a less than or just a greater than, you have to go through the test, but you could also use confidence intervals if it's a two-sided test. Okay? Now, I told you I'd talk a little bit more about power, so in our last minute or so, just to remind us, the chance of making a type 2 error, which is beta, right, is when we fail to reject the null when it's false. So that's like saying we accept it, but it was false, so that's why there's an error there. Well, if your null is false, then it needs to be rejected, which is why power is 1 minus beta. Okay? So power is the likelihood that a study will detect an effect when there is an effect to be detected. It's the chance that you did the right thing. Okay? So if the power is high, the chance of making a type 2 error goes down, right? The chance of making a type 2 error or concluding that there is no effect when in fact there is one goes down. There's an example in your book that you can play around with and test out more information about power if you're interested in knowing more.